Hello everyone, my name is Eda Goldenberg. Welcome to Nano Open webinar, which is organized by Sabancı University Nanotechnology Research and Application Center. It is our pleasure to introduce Professor Şener Oktik, who is our guest speaker today. Professor Oktik graduated from Ankara University with a degree in physics, and he received a master in applied physics from the same university. He received his PhD degree from Durham University, Department of Applied Physics and Electronics in 1982. Professor Oktik became associate professor in 1986 and full professor in 1995. During his academic career, he has worked as a lecturer, research scientist, senior researcher, and administrator, senior administrator at Durham University, Lecce University, Stuttgart University, Selçuk and Muğla Universities in Turkey. Professor Oktik served as the third and the fourth term of president, rector of Muğla University between 2002 and 2010. His industrial research and technological development, during his industrial research and technological development career, Professor Oktik has worked as a senior research scientist, technologist, and senior executive at BP Sunbury Research Center, Imperial Chemical Industries, PLC, and Center for Solar Energy and Hydrogen Research, Baden-Württemberg in Germany. In Turkey, he was a consultant for several companies, and he involved in their R&D activities. Professor Oktik served as the president of Research and Technological Development at Turkey Şişe Jump Company between 2012 and 2020, and he is serving as a member of the board of directors of Şişe Jump currently. And he has been a member of many non-profit organizations and occupational organizations, and including advisory committee of International Commission on Glass, Conference on Coatings and Glass and Plastics, the Center for Functional and Surface Functionalized Glass in Slovakia, Turkish Clean Energy Foundation, Advisory Committee to Turkish Science, Technology and Innovation Policies Council. And this list is going on, still very long and impressive. And Professor Oktik is presenting Turkish Physical Society at the European Physical Society, and he is the honorary chairman, Turkish Solar Energy Industry Association. He is author or co-author of over 100 scientific and technical publications. He is inventor, co-inventor of 2 world patents, and serving as a senior lecturer researcher at Kadir Has University since May 2020. Now, please let me welcome Professor Oktik to share with us his seminar on nanotechnology in photovoltaic energy conversion.
Thank you very much for this long introduction. Probably it wasn't necessary, but I do thank you, and of course I do thank Sunum and Professor Fazilet Vardar for inviting me for this seminar and the chance to really touch upon nanotechnology in photovoltaic energy conversion. Before I start, probably I should put this presentation in the full screen mode. And probably they see better. Nanotechnology in photovoltaic energy conversion really has 2 parts, the photovoltaic energy conversion and nanotechnology. These are most important routes really in recent years for the societies, for the governments and the energy sector. If I look at the presentation outline, what I'm planning to do, I'll touch upon the saga of photovoltaic energy conversion. And I will give a brief introduction to current facts and figures of photovoltaic energy conversion. Then the nanotechnology and photovoltaic energy conversion. Of course, there's a nanotechnology in the crystalline silicon cell-based nanotechnologies. and organic photovoltaic technologies. And of course, my heart recently very close to transparent organic photovoltaic cell technologies, and I'll end up with some conclusion. This is my disclaimer. All the data I really collected and presented in here is the sake of really this presentation, and it shouldn't be taken as a role, any reference for future use of anyone. Probably I should start with this triangle of science, technology, and industry. Sometimes it is called holy triangle. It is really the holy one. In the science and knowledge development for photovoltaic, the studies in inorganic and organic materials are very, very important, and the device design has been developing significantly in recent years. On the technology side, applications of those findings of basic research was taken quite seriously and at the technological level and developed towards the pilot production line. When you think of a technology readiness level, really it goes step by step. Of course, industry should be in here to take up this technological development into a business. So industry important for the business development in photovoltaic technologies for the power industry. This really defines the progress in photovoltaic energy conversion in value chain. So there are some certain milestones in this story. When you look at the scientific part, you can really list hundreds of milestones. But what is much important for me to understand, improving the really understanding and really progressing by better understanding. Probably we should mention Albert Einstein photoelectric effect to understand the photovoltaic business, because he was the first one to explain very clearly the interaction between light and matter. Then later on, there was one entrepreneur in America really invented the solar cells to convert sunlight into electricity. And of course, discovery of PN junction by Russell Hall was another important milestone in this scientific development. If you look at the technological developments within this triangle, I call it a holy triangle of science, technology, and industry. When you look at the technology, the Bell Labs really have won the important milestone by really taking up research on practical solar cells preparation for their telecommunication purposes. And they managed in 1954 to produce 4% solar cells, but the actual cost was $1,000 per watt, which is not feasible. Of course, in those days, the cadmium sulfide base, the cadmium sulfide, copper sulfide heterojunction was very promising one. It took long years really to study, but at the end, because of the stability problems, left behind. Actually, my PhD was on cadmium sulfide, copper sulfide solar cells in 1980s. Then actual progress really done in the industry by technological development, industrial technological development by Hoffman Electronics. They initially had a 9% efficient cell, then 10, then 14% in 1960s. Of course, some of those work has been used in the space satellites. The first space satellites, Vanguard, still running around, I think, using photovoltaic power. In the other side of the water, Sharp in Japan in 1963 started some technological development. But all these through 1960s, the price was still wandering around $100 per watt, which was not feasible for the power industry. So it did not really develop that fast. And business development side really started with the 1970s oil crisis. Probably most of you know, the big companies like BP, Shell, Mobil, Exxon started work on photovoltaic research and technological development projects. And in 1970, the one guy, really sponsored by Exxon, managed to really introduce a new grade silicon, solar grade multicrystalline silicon for solar cells, and the cost down to $20 per watt. Following that, the big step was by Arco, the biggest company at the time for photovoltaic, managed 1 megawatt peak year production. It was a big news in 1983. And starting from 1980s, there was unprecedented scientific and technological progress, actually, in each component of the sector, from solar cell, inverters, etc. And the production capacity has grown significantly, and cost reduction was very, very significant. Where are we at the end of 2020? Probably I should share some facts now with you. Remember that 1 megawatt production capacity at the beginning of 1980s. In 2020, after 40 years, the actual world production capacity is around about 137,000 megawatts, 137 gigawatts. And most of them really was installed, as you can see in the field in 2020, actually more than the production. So currently, now 20 countries have more than 1 gigawatt peak in a year installment. In a year, 20 countries really installing more than 1 gigawatt. But when you look at, most of them are silicon-based. Monosilicon is quite big one, almost 90, multi almost 40. Thin film is fairly small. All in all, where are we? Currently, you got something like 760 gigawatt photovoltaic power capacity. Okay, probably one, I should mention, what is the total power capacity of the world, including nuclear, thermal, hydro, whatever you can think of. It is 7,500. So still looks a bit small compared to that, but it is still getting there. But when you look at that, more than 5 countries has more than 40 gigawatt installation, 12 countries more than 10. In Turkey, reached to 7 gigawatt installation all over Turkey. But as you can see, China is leading the actual amount of installation of photovoltaic in the world, followed by USA, Japan, etc. You can see in Europe, you can see the total of Europe in 2020 has less than Chinese installation. Of course, the major part is actually what are the efficiencies doing in those solar cells. As you can see, the developed photovoltaic solar cell measured in NREL, the best lab efficiencies, but I should express that these are the best cell efficiencies, but not the stable commercial efficiencies. I'll mention what is commercial efficiencies there. As you can see, for multi-junction, you can go up to really getting to close to 50, 47%. And most of them really is more than 20%, either in silicon or thin film side. And when you look at actual summary, best cell versus best module, because you lose a lot through cell to module when you produce cell to module. I will be really giving into detail a little bit later. What is the importance of nanotechnology to really reduce that difference, how we can improve efficiencies and efficiencies of cell and modules. As you can see, you can get a silicon monocrystalline cell up to 27% now, and you can have modules around about 25%. For multi, it's a little bit less, and as you can see, thin films are catching up. But there are newcomers, organic ones, And the perovskite is a very important part coming up, reaching almost 21%. So how we can really cluster all those different cells? This is the general accepted methodology to have 4 generations for photovoltaic solar cells. In the first generation, monocrystalline and polycrystalline silicon are the major ones. And currently, more than 95% of the current photovoltaic system is first generation solar cells. In the second generation, thin film technologies, amorphous silicon, microcrystalline silicon, CIGS, and cadmium telluride. And then the third generation solar cells, you've got the disensitized solar cells, organic and polymeric solar cell, perovskites, quantum dot cells, and multi-junction cells tandems. In the fourth one, low-cost, flexible polymer thin film and transparent photovoltaic cells. These, in this generation, they employ nanomaterials, metallic nanoparticles, metal oxide, fluorines, and the derivatives, graphene and its derivatives. We'll be really discussing on those, what are the effect and what sort of impact they will have for the future. Okay, let's look at the facts a little bit more. If you go to market and try to buy photovoltaic silicon cells, today you can have cells between 19% and 23, 24%, but you pay accordingly. As you can see, the prices. The efficiencies today, again, as I said, between 20 and 24, but within 10 years, we're expecting to go up to 29% tandem cells with the help of nanotechnology, of course. And as you can see, there are different kind of cell design, different kind of technologies, starting from PERC-X, heterojunction cells, tandems, etc. But they have different roadmaps for the future progress, but most promising one are the tandems for the future. Well, when you look at the current prices, these are the prices on the 2nd of June this year, just a week ago. Prices changes according to cell qualities and efficiencies between 10 cents and 15 cents per watt. Okay, it has been developing in the really ingots sites, wafers, cells, model design, size, and shapes. In all those, you'll see in a minute, the important things are including nanotechnology in the progress of those manufacturing, from ingot to wafer to the cell, of course, to the modules. And these are the really modules you can buy on the current market from different companies. As you can see, the actual power of each module goes up to 400 watts. Now, if we go one back, for instance, you can see in 1930, we're expecting actual module powers between 1,000 and 2,000 watts. So there's a sort of really almost 2-3 times more than today's modules. So there's a big jump in this field. And these are the expected stabilized module efficiencies for the future. You can see tandems going to 26. And the price-wise, as you can see, modules can be really reduced in price every time you increase the volume 100% or double the volume. The price comes down 25%. It has been holding this relationship more or less 40 years. But the prices of modules, again, depending on the module characteristic and size, changing between 20 cents to 26 cents. For the future, when you look at next 5 years, it is expected that today's total installation will be doubled. And of course, within this, there are significant expectations for improvement in each chain of photovoltaic value chain. When you look at today's situation, as I said earlier, actual thin film more or less really lost the importance in the sector, but please do watch it, because this area will become again important applications with the help of nanotechnology in the near future. When you look at the total power photovoltaic power installation across the world, mostly power plants. Rooftop installation is about 35% of the total today, and it won't change very much within next year. But there's a newcomer. Although looks small now, this is called building integrated photovoltaic. I will explain why it is important, what is the potential there. Rooftops are available, commercially available, and a significant percentage, almost I think in the world is 15% of the total is rooftop. But in Turkey, I think it's only 1 gigawatt rooftop among that 7 gigawatt installation. While preparing there, really, I went to the really 10 years back or 17 years back, I really put one of my early projects in Muğla University. As you can see, in 2004, I put 25 kilowatt rooftop on the student cafeteria. This was the first in Turkey, I think. Then again, same year, I put some facades. This is not really integrated, this is applied. Changing the facade, we really decided to have some photovoltaic 40 gigawatt. I think they are still working. Facade is important, but if you have non-transparent, it's not really that convenient with the existing architectural changes of the world. So what we need is a truly transparent PV system. This is the emerging technology and at the development stage in relation to nanotechnology. Why I am really expressing that very much? Because of the actual architectural changes. These are the highest 14 super tall buildings in the world. Their height is higher than 300 meters each. But when you look at it, all of them are really glass. They are glass faceted buildings. So just imagine and dream if they're all PV, but transparent PV, how much area you have to be able to produce electricity where you live. This is an important step for the photovoltaic sector. And believe me, it will be coming not far from today. Next 10 years, we will be seeing lots of building with transparent PV on their facades. Okay, nanotechnology. I couldn't help really put one of my hero in physics, Richard Feynman's picture in here, lecturing in 1964. But he can be, he is really counted as a father of nanotechnology with his famous talk, "There is a plenty of room at the bottom." The idea was manipulating matter at the atomic level. Just after that, another milestone is 1974 in nanotechnology, using of term by Noria Taniguchi. And he explained that the actual material can be processed, separated, consolidated, and deformation can be established at the atomic and molecular scale. And nanotechnology has a really big impact for the coming years. In photovoltaic energy conversion, of course, designing nanoscale surface structure to improve the tunable absorption and reduce reflection, transparent low resistance for the contact for charge collections, nano coatings for improved efficiency, designing innovative solar cell structure for transparent, for instance, nanowires, photocatalysts in solar cells, etc. You can really increase the list to be applied in the photovoltaic energy conversion. If we go back to really standard first generation solar cell preparation from polysilicon to modules, you can really introduce some part of progressing nanotechnology in their production, some technological development, but it's not really easy to go all through within the given time. I already really used 28 minutes of my time. I will give you some teasers on the cell, for instance. Black silicon, silicon nanowires. These are very important because you know the properties of silicon and their refractive index creating some problem. And by producing silicon nanowires or creating black silicon by etch, you can really play with the absorption and reflection at the nano scale. And actually the new part is the horizontal grown silicon nanowires structures. Lateral growth of nanowires on the silicon surface will help significantly in really improvement of absorption and reducing the reflection. On top of that, of course, one important concept is coming into metal nanoparticles. How we can really combine metal nanoparticles with this nanosurface structures. The idea is really that refractive index of 3.5 at 120 nanometer and room temperature, this causes reflection losses. If we employ a sub-wavelength nanostructure texture, we can reduce a bit. And actually, since you know the silicon is an indirect band gap, the low absorption coefficient, especially below 800 nanometer. How we can enhance this? Again, nanotechnology coming here. If we really introduce metal nanoparticles really on those nano texture surface, what happens really? You start with really the delocalization of the conduction band electrons. They start oscillate with the coming waves, and surface plasmons propagate to the interface of the device, and this create really plasma resonance, near field enhancement plasma resonance, which will affect significantly your efficiency. You can see how nanotechnology can really help the progress of even the first generation solar cells. Some recent results, you know, they use the gold metal nanoparticles, and they really plotted in 3 different conditions for 3 different structures. But as you can see, when you go to Lambertian limit, which is 4n square, within that, in the infrared region, you can see you can even really beat the Lambertian limit. You can see the absorption of bare silicon, absorption of bare nano textures, and you see what happens when you really add the metallic nanoparticles on those nano surface textures. It is an important progress, important area, and believe me, significant research and technological development work is going into this area. Okay, the second important milestones, there are 2 important Nobel Prize really. Although scanning tunneling microscopes did not get Nobel Prize, but it was an important milestone in really playing with the surfaces at atomic scale and manipulating them. And in 1984, discovery of fullerenes and their derivatives was the 1996 Nobel Prize, was a very important step for organic photovoltaic. As you know, there's buckyballs and its carbon nanotubes and other shapes and size in fluorines is important area for chemists, physicists, and material scientists to work in. The other important milestone is the Nobel Prize, again in chemistry, synthesis and controlling the doping of polymers. Of course, another thing we should mention is the discovery of new class of carbon nanomaterials, carbon dots, C dots. These are very important milestones in nanotechnology. For the electroconductive polymers, you can have organic semiconductor, organic metals, organic insulator, so you can have organic structure all over. What are the advantages of organic semiconductor and photovoltaic production? First of all, they are low weight, they are flexible. You can tailor their band gap. And there is a potential they can compete with existing PV efficiencies. Actually, the materials is abundant and non-toxic. And there are major technologies to deposit them in the large area. And they are low temperature processes. They are very efficient in material use. Would you believe you can have 1 square meter organic semiconductor with 1 gram organic material? And you can manufacture on flexible substrate. You can really increase the number of points in the list, but there are certain advantages. And there are 3 types of organic photovoltaic cells: small molecule OPVs, polymer-based OPVs, and dye-sensitized OPVs. Dye-sensitized OPVs is a hybrid, organic and inorganic. Okay, probably I spent a couple of times in the basic of organic photovoltaic cells. For the analogy, if you know inorganic semiconductor, valence band is the highest occupied molecular orbital HOMO. Conduction band is the lowest unoccupied molecular orbital LUMO. And energy gap in inorganic is the energy gap between HOMO and LUMO. How it works? Simply absorption of incident light leading to exciton generation. Exciton binding energy is, as you know, between 0.3 and 0.5 electron volt, fraction of electron volt. Then this exciton diffuses to donor-acceptor interface, and they dissociate exciton across the interface, then charge carrier transport and the collection. It is very much analogous to standard PV operation. But the difference is actually everything happens in 100 nanometer active area. Actually, in those cells, the active area is only 100 nanometer. And all the components, these are donor polymer, these are acceptor molecules, and they are all really entangled within 10 nanometer. Everything is at nanoscale. So the technology is nanotechnology. When you look at the early ones, there was a bilayer OPVs, but there were problems with that. Bilayers was too thin for low absorption, too thick for the efficient exciton dissociation. Then efficiency limit was too low. Then in 1995, new kind of a design introduced for OPVs called the bulk heterojunction, BHJ OPVs. This is much more efficient. Currently, the efficiency is using a different kind of molecules reached to 18%. Simply, from 2015 to 2020, there was some sort of significant improvement in efficiency. But initially, most of the polymers are blend of fluorines as an acceptor material. And recently, non-fluorines are introduced, NFAs, and this have significantly improved with some problem. Of course, there are some important advantages. The best of one is a tunable band gap. You can tune it according to your demand. This is the highest one so far, which 18.22%, almost over 18% efficient. As you can see, the device is made of, I'm not going to go in the detail of the chemistry, I'm not a chemist, but you can see the actual molecules used and how they interface, and their band diagram is given in 6 slides. But there are sort of pro and cons. Non-fluorines have better efficiency. There are limitations in about 11% with fluorines. But the problem is, with the current technologies, the actual stability of OPVs, organic photovoltaics, much stable for fluorines than the non-fluorines. But significant effort, I would say, will solve that problem. We'll have a better stability in higher efficiency OPVs. Now, I like to go back to sunshine, solar radiation, and photon flux. Okay, we need to really use certain part of this spectrum not to really affect our vision. So it could be transparent. So to give this discussion, I'll give you the actual photon flux. The photon flux is around about 4 times 10 to the 17 per centimeter square per second. When you really integrate that, you can see most of the photon flux, almost 73% in the near infrared region. There's only 5% in the ultraviolet, and the visible region is 22%. So when we look at it to see anything, what was our vision? As you know, we don't really although we say, okay, we see between 390 nanometers up to 780 nanometers, depending on the source you use, they sort of change a little bit. But do we see all of it? Or our vision are really covering all? Actually, the vision to human eye have 3 different concepts. One is photopic vision. This is the vision under the light condition bigger than 3 candela. And the peak intensity is about 550 nanometers. There's a mesopic vision. This is the light condition from 3 candela to very small 0.1 candela per square meter. And there are scotopic vision. This is a low light condition, less than 0.01 candela. So when you design something, you have to consider those. At the end of the day, what you're serving is the end user. So you should have a visual comfort for the end user if you are going to design transparent photovoltaics for building facades. I'm not going to go in detail, time is getting short. You can really calculate the average visible transmittance, and you can talk about the absorption region for TOPV. And the other important thing with the visual comfort is the haze. You don't want to really haze in your window, and your color rendering index should be in the correct region. Actually, these are the area we very much struggle at Şişecam when we really provide coatings on glass for energy conversion, like all the coatings we have. Okay, go back this, and we can say, if you're gonna design a transparent photovoltaic, aesthetic qualities, average visible should be over the 45%, color should be neutral, and currently efficiency should be, as a stable efficiency, more than 10%, cost should be low, production should be in industrial stands, thickness could be around about 1 micron. Can it be done? Yes, because with the nanotechnology, we can really aim to those regions. Let's have a look. I go back to my dream. If you go really cover all those buildings with the organic photovoltaics, how much we can really progress. There are three types of transparent organic photovoltaic. One is wavelength selective transparent organic PV. These are the visible range limit transmission more than 45%. There are luminescent solar concentration system, and there's a novel design. Actually, this is using molecular design as well as device design. This is a very clever one. I thought it is developed in MIT, and now it has been pilot production line in Japan somewhere. If you start the luminescence concentrators, LSC system is a light absorbing, emitting and waveguiding, and conventional photovoltaic conversion. So in LSCs, you use the conventional photovoltaics at the edge. So what you do really, you really direct all the energy, probably changing the wavelength to the side to convert the electricity. So you use the luminescence material, luminophores, dyes or phosphorus, embedded in the transparent polymer on the surface. And this absorbs UV and near infrared, and through the waveguide, you send to the edge of the windows. This is how it works. Again, probably I should not really go much into detail because I need time for the rest. This is the performance of that. How you calculate this, again, optical conversion efficiencies. You can really, it's a little bit different calculation than the standard cells. What I like to really talk on as a last couple of slides is a holistic approach to the transparent organic photovoltaic cells. So what they did really, they've got 2 different cells and the mirror for reflecting the waves. As you can see, significant number of nanotechnologies introduced, and they allow this photopic range clearly out, and they really use rest of the spectrum to create device. This is the structure of this transparent organic photovoltaic holistic system developed in MIT. They use, as you can see again, buckyballs as an acceptor that they're fluorine. Now they have got a better solution, I think, recently. But they manage to produce more than 10% efficient cells. Currently, there are different companies producing commercial transparent photovoltaic modules. Solaria and Unix and Ubiquitous, some partner Polysolar, etc. But Ubiquitous has 9.8%. 5Z technology developed at Delft University in Holland, but they use a luminescent solar concentrations, LSC, and UBQ solar windows. They use the quantum dot laminated glass. There's also bright solar. So, all in all, as you can see, this area has significant potential because of the actual available surface on the facades of buildings and the future architectural changes of the world. Even you can see in Turkey, all glass facades. So if you can really produce electricity out of those, it will be great. But we need the help of nanotechnology to overcome this efficiency barrier and the problem with stability of these devices. Final remarks. This is a promising area. There are challenges. I'm not really gonna read one by one. The challenges I listed in here, but at the end of the day, you need a device which is pleasing the end user in their aesthetic and their cost. I do thank for listening to me. I passed five minutes from my time. If there is any question, please let me know. I'll try to. Okay, thank you very much.
Professor Oktik, thank you very much for your interesting talk. And as you pointed in your talk, I hope that the research will go on photovoltaics and nanomaterials together, nanotechnology. And if you have any questions, we can get them, or you can write in the chat box.
I do hope I did agitate some questions in someone's mind to look into differences and possibilities. The chat.
Is there any questions?
Şener hocam.
Yes, I'm listening.
Yeah, just I'm wondering, how promising the use of fullerene-based photovoltaics. Are they suffering from, any kinds of, the moisture or unstable, for a long time? Do you think, that for future it is the best promising candidate?
Well, hocam, fullerene-based transparent photovoltaics has been developed, as I said, by MIT and another team in the United States. And actually, I was in contact with them. And at Şişecam, we tried to really communicate with them. And all of a sudden, they stopped communicating with us. Then we realized they really have an agreement with the large glass company in Japan, NSG. And I know in my information, they are producing modules at the pilot line. It looks that the actual moisture problem can be solved by better encapsulations or other ways. But as I said in the presentation, there is a limit in efficiency, achievable efficiency in fullerene-based organic photovoltaic. That's why people are really going from non-fullerene molecules.
Thanks a lot, hocam.
But it's on the line coming. So the problem is solvable.
Yeah. What was the group, the James Thor's group? Who was the person in MIT?
Well, if you go to the slide, actually, you can see the reference.
Oh, it is my bad. Yeah.
I can tell you from the slide, I cannot really. Actually, the guy was Richard Lunt and Vladimir Bulovic group.
Thanks a lot, hocam.
Yes, I'd like to hear more questions.
Can I have a question?
Yes, yes.
Yes, thank you for your presentation, Professor. And I have two questions. One is about Şişecam. Do you have a production of conducting transparent oxides, FTO or ITO glasses, or you tried or before?
Commercially, no.
Commercially, no, but you try. Okay.
But I mean, we can produce. We have lots of at experimental stage. We have, for instance, one of the projects we did with European Union was fluorine-doped tin oxide. And we achieved significant properties for that. It was really competitive. But the actual market was not for us, for Şişecam, so we have not really have any commercial product for transparent conducting oxide, but it's easily done. It's well-known technologies.
Okay. And the second question, actually, it will be nice to hear some comment about the role of governments. I mean, in your triangle, you mentioned about the technology and the research centers, but how about the governments? How should they take a role in this triangle?
But in I'd like to really talking on this holy triangle. Actually, of course, the industry, technological development, and the science and technology should be supported fully. I believe for fundamental sciences, there are significant steps by the state over the years. It has been changing for photovoltaic. For instance, I remember in the early days when I first really tried to introduce this photovoltaic in 1995, 1996 in Turkey. I went all around and they were laughing at me. Actually, when I really installed some photovoltaic system at Muğla University, they were laughing. They said, okay, it won't survive, it won't survive. From there today, the support is significant in research and in industry. But the policies, is it correct? I don't know. If you remember, if you're following the recent tenders for photovoltaic systems, it's fairly interesting. You know, there are investors, entrepreneurs, really giving price around about 20 Turkish kuruş per kilowatt. This is very, very, kilowatt hour. It's very interesting figure. So the expectations in the public is high. My belief, if you don't have the public perception in the right directions, you cannot really affect policymakers, states, governments. Everything is down to the public perception, the end users. I think in Turkey, the end users start believing in photovoltaic, and it will change. You can see different subsidies will be coming again. And the support for R&D is not negligible, it's significant.
Okay, thank you very much for the answers.
I hope I'm not being too political.
No, I mean, you are strong experience between the RD and the also academic science, academic yes. side. So I think you should talk about these things, or you should give the direction, maybe some politics.
Yeah, I'm in some of the committees. Really, I put my opinion clearly and bluntly, honestly.
Okay.
Thank you very much, Professor. I have a question. Can I ask?
Of course, yes.
Yeah, thank you so much for the informative talk. And my question is related with the QD-based photovoltaic solar cell development. Is there any work in which Şişecam is working on the development of QD-based solar cells, especially for transparent-based?
No.
No.
Well, honestly, for photovoltaic studies or any study related to photovoltaic conversion, only area I managed to convince Şişecam is the anti-reflective coatings and development anti-reflective coatings on glass for supplying cover glass for modular makers in Turkey and outside. Apart from that, I had some, it's a bit confidential, but I had some attempts to really pull them at international studies and companies and production, not with successfully. I think I couldn't success. There is no, I'm sorry. There is no work on QD, no.
Thank you very much.
You are working on QD?
Yes, we are basically using quantum dot for preparing nano biosensor for point of care applications, especially for disease diagnosis monitoring. But QD can be used. It's a very interesting talk. I got to know a lot of information. So I would really like to see what kind of QD should be used. It could be like C dot type or CD based QDs. and their efficiency. So I think it is really interesting and informative talk. Would you like to comment on type of QD which can be more suitable for the development of transparent based solar cells?
I couldn't really. If I say anything, it won't be so informative because probably you know much better than me on the QDs and the work in there. I wouldn't really go over my knowledge on that. No, I'm a photovoltaic guy.
Great. Thank you so much. It was really interesting. Thank you.
Okay. Is there any more questions?
Şener Hocam, I think if we will share your information in this recording, so if is there any questions, we will contact you. And we thank you once more for this interesting talk and sharing with us your information, all the information on photovoltaics with us.
As a last word, I do thank once more to Sunum and all the people putting effort to put this webinar together. Thank you very much. And I like to announce that currently I'm with academia again. I'm at Kadir Has University. But any student wants to really ask questions or have some suggestions, please do contact me. My email is in there. I like to work with young people at Sunum too. I'm open. Thank you very much.